Okay, time to get started. We're recording a new chapter for today. Chapter 7 is kind of the second half of vector calculus in some sense. It's sort of roughly speaking, it's going to be kind of a three-dimensional version of vector calculus. It'll not quite that simple, but some of what we did in chapter 6 is three-dimensional. Anyway, we do have to develop some machinery first. We're going to have to define something called a surface integral. Actually, a couple of different kinds of surface integrals. And in order to be able to do that, we're going to have to be able to talk about parametric surfaces. So that's where we're going to start off. So the idea of what a parametric surface is, I'm going to say, is kind of what you might expect. Remember, a parametric curve gives position as a function of one parameter. A parametric surface gives position as a function of two parameters. Right? And if you think about it, I mean, if you were to dial back and think about parametric curves, why is it that a parametric curve typically, creates a one-dimensional curve? Well, it's because there's one parameter going in, and one parameter going, in some sense, like a one-dimensional interval on the t-axis is what goes into the function. So you kind of expect a one-dimensional thing, namely a curve, to come out. So likewise, analogously here, with two parameters going in, shouldn't you expect two-dimensional output? So here's an example of what I'm talking about. Now this is old. We didn't say the term parametric surface at the time. I think we described this as being a parametrization of a plane and left it at that. But it is a parametric surface. So let's think about this thing here. Some of this will be just a reminder from section 1.5, but if you know a point on a plane, right, do keep in mind that, of course, you can think of that as being a vector or a point, suit yourself. Anyway, point on a plane, and if you have a couple of vectors that are parallel to the plane, right, like that, V1 and V2, then from this, starting at the purple point, and then moving in the directions defined by V1 and V2, you can kind of, if you will, sort of trace out the entire plane. You can get from here to any point in the plane just by moving appropriately amount in the V1 direction and appropriate amount in the direction of V2. Specifically, some multiple of V1 going to be still parallel to V1 and therefore still parallel to the plane. And then from there, some multiple of V2, again, parallel to V2, therefore still parallel to the plane. And so all together, that starting point plus a multiple of V1 plus a multiple of V2 gets you to points on the plane. And notice your parameters here, these arbitrary parameters, namely S, namely how far do you go in the V1 direction, and T, how far do you go in the V2 direction. These two parameters, right, are what in some sense help you sort of trace out in both directions and thus kind of fill out the entire plane. And so position is a function of two parameters there. And again, as expected, two-dimensional image. Okay. All right. Now there is one big difference aside from how many parameters you have between parametric curves and parametric surfaces. With parametric curves, we could kind of lean on this very convenient visualization trick, metaphor, maybe, whatever you want to call it. Let's think of our parameters being time. Right? So position is a function of time. That's fantastic because it conjures this image of literally tracing. Right? If you trace your finger along some curve, then you're giving position as a function of time. Right? Okay, so as much as we like that and as convenient as that is, it's not really an option for parametric surfaces because you have two parameters and you can't think of both parameters as being time, like having multiple time dimensions. Again, that's very sci-fi. I'd watch that movie, but I don't know what that really means in a real sense. Everybody see what I'm talking about there? Okay. All right. Okay, now, big question. How do we create parameterizations. If I've got some surface given to me, some surface that I need to understand in some way, I need to do something with it. Eventually we're going to be taking integrals on surfaces. How do I create a parameterization? And side note, creating a parameterization is going to be the first step in one of our primary methods, our sort of fundamental method for computing surface integrals. The first one I'm going to show you is called a graph parameterization. You may recognize that term. We talked about graph parameterizations of curves. Right? This is shockingly similar. It's really, really the same. So, big idea, if your surface is a graph, big if, right? Not every surface is a graph, right? But if it's a graph, namely if one of the variables is a function of the others, then here's the big trick. Whatever are the input variables, let them be your parameters. And believe it or not, you're basically done at this point. We haven't yet enumerated how we're done, but we are kind of done. All you got to do, whatever the input variables, make those the parameters. Boom. So here's how we're done. Keep in mind our goal is to get position as a function of two parameters. Well, x and y are the parameters by choice. And then, well, wait a second, the z, as I have it here anyway, is a known function of x and y, which are the parameters. And so sort of by taking x equals s and y equals t and popping it into here, then there's your formula for z. And lo and behold, we have position, right? Position as a function of two parameters, as desired parametric surface. How are we doing? Everybody see how that's just sort of morally equivalent to our old graph parameterization trick for curves, just kind of one extra parameter, really all there is. Okay. All right. Just like with parametric curves, it doesn't matter which variable is a function of which other variable. Here's an example where I'm going to use y as being a function of x and z. Now, at a glance, looking at this example, this equation right here, doesn't appear that y is a function of x and z. That's just because I haven't solved for it yet, and I certainly can. Right? I can do like that, solve for y as a function of x and z. Notice I have to choose y there. I cannot solve for x. Cannot solve for z. Right? But I can solve for y. It's a function of x and z. And again, we're kind of done. My input variables in this function are x and z. So x and z are my parameters, arbitrarily chosen to be s and t. And let's see, what is y? Well, I don't really have any choice in the matter. X and z have to be s and t, which when I plug in there forces y to be that. And we're done. We have a parameterization. Position, right? Position x as a function of two parameters, s and t. Everybody happy? Questions, feel free. All right. Okay. All right. It doesn't even have to be rectangular coordinates. Now, we saw something along these lines with parametric curves as well. But we did that in polar coordinates. We can do the same trick here. The one additional little step, in some sense, is that you do have to write down the conversion formulas for whatever coordinate system you're using. So here's our standard spherical coordinate conversion formulas. You write that down. Notice that sort of sets us up to have position. By the way, when we talk about parameterizations and position as a function of blah blah blah, it does need to be rectangular. Right? When you got a parameterization, the whole point of having a parameterization is so you can use nice features of rectangular coordinates, like how the derivative is interpreted and that sort of thing. So rectangular position, right now written as a function of three parameters, and I can eliminate one very easily. Again, having the graph parameter, having it be a graph, having one of the variables solved for, means that I can plug in for it. Right? And so while my conversion formulas initially gave me position as a function of 3 parameters, now I have position as a function of 2 parameters. And in fact, I didn't even have to make up new parameters. I didn't have to make up like an S and a T or a U and a V or anything like that, because I started off with parameters that are already not X, Y, and Z. And so there's no sort of confusion of variables issue. You can just leave it as position as a function of phi and theta. Okay. All right. Is everybody all right with that? Okay. Okay. All right. Now, that's the graph parameterization is one tool for creating parameterizations. Y'all know my tool full of toolbox metaphor. That is how parameterizations work. It's not that there is a single way to do it. It's that there's various different tools that you can use to construct your parameterization. The graph parameterization is a great tool, fantastic tool for creating parameterizations in some cases. Other times, not so much. And so we need other tools. Here's my next one. You may recall we used vectors to construct parametric curves. Remember the bicycle, right? We've got a bicycle wheel rolling down the road, and there's a reflector on it, and the reflector makes this kind of weird, sort of jaggedy, sort of, weird, let's leave it at that, pattern. How do we parameterize that weird curve? And we broke it down as a sum of much simpler vectors. So that's what we're going to do here just for a surface. So here's the idea. We start off with this. Let's see here. What am I going to do? I'll do this in green. Start off with this surface right here. Notice that's an upside down paraboloid. Right? And then let's see here. I'm going to suppose that this is, think of this as being the top of someone's head, right? And then there's hairs of length 1. Hairs of length 1 that are pointing outward and perpendicular to the surface, kind of like that. So again, perpendicular to the surface. And the tips of those hairs. In other words, in some sense, what the hair then makes that person's head look like. That's what we want to try to understand. How do I parameterize this purple surface? Right? Everybody see what I mean? Okay. Right. Let's see here. We've never seen a surface described in this way before. So we don't have any, I can't say, oh yeah, the purple surface, it's, is this definitely a paraboloid? Actually, it's not a paraboloid at all. I think I could probably persuade you if you were to sort of, take this to an extreme length. Imagine that instead of these hairs having length 1, if they had length 50, right? It was just hairs pointing out, in some sense, in every direction, all by kind of the same amount. And sure, some of them are a little higher up and some of them are a little lower. But compared to a length of 50, you get something that's almost spherical. So it's not going to be a paraboloid, right? Depends on the hair length, and it's just going to be some random weird thing. And we're going to parameterize that now. So first of all, we're going to focus on the green surface. I point out that the green surface is a graph. And if I wanted to parameterize the green surface, in other words, if I wanted to find position, this point here on that green surface as a function of parameters, graph parameterization, we've parameterized that the head, you might say, the skull, the scalp, whatever. All right, is everybody good? Okay, so here's the thing, though. Yes, it's a graph. You can see it's a graph, but I can also take this equation and I could rewrite it by taking these terms and moving them to the other side, or various different ways you could shuffle things around. And I could rewrite it as being a level set of missed. Level set of this function here. All right, now this is some chapter 2 trickery, and make sure to remember that if you have a surface described as a graph of one function, you could reinterpret, by this little bit of algebra, you could reinterpret it as being a level set of a different function, a specific, particular different function. And reinterpreting as a level set opens up the door for us to now use the calculus of level sets, which, as it turns out, we're going to need in a second here. All right, before I go on, is everybody comfortable when I say it's a level set of that function? All right. Okay, so here's how we're going to use the calculus of level sets then. Don't forget, if you have a function whose level set you're looking at, then, let's see here, I'll use red. The gradient of the function whose level set that you're looking at is always perpendicular to that level set. And keep in mind, our level set is in fact the original green surface. It's just sort of at a different point of view on that original green surface. So, gradient of G is perpendicular to the level set of G, namely what we're looking at. So this gradient here, and of course you can compute that. This gradient you can compute. Easy algebra. Very useful because it is pointing in the direction that the hair is going. And so this is our kind of foot in the door to understand which direction the hair points. Okay, and now don't forget the way we have things set up. X and Y are S and T. And so with that in mind, we can rewrite our gradient like that. Okay. Except, here's the thing though, that's not what I wanted. What I really wanted was not that whole vector. I just want a unit vector pointing in that direction. And so dividing by its own magnitude gives us then what this unit normal vector is here. And now I've actually got everything that I need. Let me clean up the mess from all the stuff that I don't need anymore. There's a lot of stuff I don't need there. I've got a formula for points on my inner surface. I have a formula for the vector describing how the hair moves perpendicular to that surface. And all together, points on the outer surface are just, green plus orange. That make sense to everybody? What do you think? Is everybody happy? So, for whatever it's worth, I don't know how I would do this problem without breaking it down into simpler things, right? These purple points, what do we know about them? Oh my gosh, I mean, it's really hard to say what we know about them, except I can conveniently say, look, I know that they come from points here, and I know that from there I go in a certain direction by a certain distance. And so breaking it down as a sum of two vectors, much easier than trying to understand the thing by itself. Okay. All right. There you go. All right, next example. Next tool for your toolbox. Sometimes, depending on what you're trying to parameterize, the example I'm going to use here will be a torus, which, by the way, is a sort of a surface of a donut, if you will. All right. So what, in fact, specifically, this is what you get when you take a circle in a vertical plane hinged on the z-axis, right? Distance a from the center, radius b, as I have it drawn here. And when you then rotate that around the z-axis, that will generate a torus. And question, I'd like to parameterize now that specific torus. Okay. So the trick here, just like it says here, is create a coordinate system. So imagine that this is a weird-shaped planet, and you live on this weird-shaped planet, and you got to be able to talk about where you are on that planet and be able to communicate with other, people living on that torus about where you are and where they are, etc. So, for example, we do this on Earth with longitude and latitude. That's a coordinate system. A way of talking about where we are. And how would they do this? What would be a natural, convenient, simple coordinate system for this surface? And here's my idea. I think you'd, roughly speaking, do longitude and latitude. So if you're at a point here, right, then you can talk about how that rotates around. In particular, you'd compare this point. Arbitrarily, I'm going to say, where does it sort of rotate to over in the XZ plane? Let's talk about that blue point. And there's two angles then that I can talk about. One is from the center, if you will, of the kind of the doughy part, this kind of the handle, if you will, of the donut, right? From that center there. First question, what is this angle? I'm going to call that T. That's going to be one of my coordinates, right? That defines this blue point. And then from that blue point, you can ask the question, all right, well, how far do I have to kind of go? How much angle S do I have to rotate to get to where I actually am? Right? And these two angles, kind of a longitude and a latitude, kind of, sort of, if you will, in this, weird donut-shaped planet. Everybody see what I'm talking about? Feel free to ask if you have any questions. Okay, all right. So my motivation in this case was, I don't know, this isn't a sphere exactly, but, longitude and latitude are natural things to talk about when you see circles. I see a lot of circles in this picture. So that seemed like a reasonable choice. With other surfaces, you might have a different pair of coordinates that seem natural. The most convenient way to describe locations. And just set up your coordinates however is most convenient for you. And with the coordinates set up, then you can just start doing sort of vector analysis. And here's the way I'm going to do it. We talk first about this blue point, right? Previously noted. Whoops, missed. Okay, and it's that vector a comma 0 comma 0, and then plus this vector, and this green vector here is maybe a little bit harder to talk about. If you think about it, that green vector, it kind of rotates around depending on what the angle T is, right? And I appeal to your memory of trig and unit circles and that kind of thing. So if that distance is b per the setup, then as it rotates around, as T being your angle, you're going to get cosine and sine for x and z. And of course, these vectors here, keeping in mind we're looking at this point, the blue point's in the xz plane. There's no y component to that green vector. So it's just cosine and sine for just the x and z coordinates. What do you think? All right with everybody? So that blue point here is, what do we got there? Purple plus green. Okay. All right. Next, and let's see here. Go ahead. This is the convenient sum there. Next thing, once we have that blue point, keep in mind, the blue point is what our actual location in some sense rotates into. How then am I actually going to get from there to the actual point, X, that I'm interested in? Well, that's going to be, I'm just going to rotate by that angle, S. And rotating counterclockwise around the Z-axis by an angle S is accomplished by this matrix. Now here, I've deliberately left some details for y'all to think through. I want to remind y'all that there's a linear algebra sort of assumption, prerequisite here. This is a linear algebra geometry problem to make sure that you understand where this matrix came from. Remember, the big highlights are reflections and rotations are linear transformations. Linear transformations are represented by matrices. Matrices are understood by columns. And the columns are the images of the standard basis vectors. So just think to yourself, all right, well, what does this rotation do, this green rotation here, what does it do to E1? Write down a little geometry, you're going to get that column. What does it do to E2? Write down a little geometry, you get that column. What does it do to E3? Well, E3 points straight up. When straight up rotates, nothing happens. So, third column, still just straight up. Okay, so I deliberately want to leave this as an exercise. Make sure that you're comfortable with this. If you are a little shaky, maybe perhaps you've forgotten how that whole images of standard basis vectors business works. Remember, we covered that on the first day of class. I know it was a long time ago. If you're a little shaky on that, perhaps come to office hours. I'd be happy to remind you, help you solidify all that stuff. Ditto the help room, ditto Porter's office hours, etc. And you can always ask a friend, of course, as well. Okay, so we're all set up then, pretty much. We've got this blue point, which we wrote down. Let me zoom out here. We wrote down the coordinates of that blue point. A little bit of vector analysis. Now we know how to do this rotation. So we literally apply the rotation matrix to the point, that blue point we computed. And all together, as a result, our purple X point ends up being that. Okay, so real quick, I want to point out this exact example is kind of in the book. Kind of. The book gives the sort of what you might call the opposite point of view on this example. I started with, hey, we're interested in a donut. How can I parameterize a donut? And then I showed you, again, an example of how you can work out and create the parameterization. The book presents this, again, kind of in the opposite way. The book starts with, hey, here's a parameterization. What is it? What does this generate? Right? And they take a totally different point of view, of course, and the result that they come up with, of course, is they demonstrate that what that parameterizes is a donut. So, in fact, all of the book's examples are like this. All of the book's examples start with a parameterization and help you understand what it is. All of my examples are the opposite. Because in my opinion, that's what we really need more. We're going to find ourselves in this class much more with unparameterized surfaces given to us and needing to create a parameterization. And much less will we have a parameterization naturally sort of coming up and then needing to interpret it. It just doesn't tend to go that way. So I wanted to show you examples where we create parameterizations as opposed to interpreting parameterizations. Okay. All right. Last trick I'm going to show you, last tool for your toolbox. Sometimes you'll have an existing parameterization that's easy, such as a unit sphere like this. By the way, how did I get this parameterization for a unit sphere? I claim that this is a spherical graph parameterization. Notice this, rho equals 1. Rho is solved for. It's a very simple function of phi and theta. So simple that phi and theta aren't even there. Right? And so following my usual procedure, you plug in the formula for rho into the coordinate conversion formulas, and this is what you end up with. Right? It'd be a good double check. Make sure you can reproduce that. Here's that same parameterization, just written sort of one coordinate at a time. Same thing. Okay, so we have an existing parameterization, and now let's ask the question of what would Yeah, okay, but I don't anymore want a sphere. Suppose now that I want to parameterize an ellipsoid, and here's the equation for an ellipsoid, right? And as y'all probably remember, an ellipsoid is what you get when you take a sphere and you stretch it by some amount in the x direction, and you stretch by some amount in y, and likewise some amount in z. And in fact, you can see here the stretching process. Right, I replaced my, let's do it like this. I replaced the x with x over a, and likewise y with y over b. Y'all remember all that stuff from chapter 2. Okay. All right. So I have a parameterization of the sphere. I want a parameterization of the ellipsoid. How can I use the one that I have to create the one that I want? And again, it's just a question of then how do I sort of exercise the deformation? How am I gonna stretch it out? What is the process by which stretching stuff out manifests itself on parameterizations? The answer here is really convenient. Not that much to it. Keep in mind, if you have your existing parameterization, notice you'll see that existing parameterization kind of already in here. There's my existing parameterization. When I stretch in the x direction, all those x coordinates just get a times as big. And so this first entry being those x coordinates, if I want those a times as big, I just multiply them by a. And likewise, second coordinate needs to be b times as big, third coordinate c times as big. So I started with a parameterization of the sphere, and I now have a parameterization of our ellipsoid. Everybody all right with that? Okay. Now, just for compare-contrast purposes, here's a different point of view you could take. Here we have equations. Now, this is still a parameterization of the sphere, but kind of written in sort of one equation at a time. Remember, back in chapter 2, we talked about another way to perform stretches. And I already kind of pointed to it here, but everywhere you see an x, you just replace it with x over a, and that will stretch by a factor of a in the x direction. So I'm going to do that same thing here now, but I'm going to do it on the parameterization itself. Just everywhere I see an x, namely, parameterization is formulas telling you x, y, and z. So when you have that x, just replace it with x over a. And likewise for the y and the z, right? The y and the z. Y over b, z over c. And that's 2. Just as well gives you a parameterization of the ellipsoid. And in fact, these are exactly the same parameterization. Doesn't at a glance look like it. Oh, let's see, I forgot to put my little purple things there. At a glance, it kind of looks like, wait a minute, on one of them I multiplied, on the other one I divided. But in fact, they're on opposite sides of the equation. Right? So if you were to solve on the right-hand side over here, if you were to solve for x, y, and z, you get x equals a sine phi cosine theta. Bam. Right? And likewise, y and z are these things. So it's just kind of a different point of view. Take your pick, whether you like to think of just explicitly multiplying the coordinates by how much you want to stretch them, or if you want to replace the variables in sort of chapter 2 style, they're going to get you to the same place. So whichever one you like better. Is everybody happy? All right. Okay. Yeah. So, again, a bunch of examples in the book. Take a look. I do realize they're all kind of backwards. They all presume the parameterization that we're going to need to find. But they're still good examples in understanding what parameterizations are and, that kind of thing. All right. And I foolishly did not bring an umbrella. And that's looking like now that was a big mistake. Oh, well. Okay. It was all sunny and stuff. I didn't... Oh, well. Okay. Okay, so now we're going to start doing stuff with parameterizations now in the last 15 minutes here. And again, there's various. I've got to work up to the what we really need here. I'm going to start off though with this idea of coordinate curves. Here's the big idea. Keep in mind, if you have a parameterization, you've got position as a function of two parameters. Okay. All right, now, innocent observation. If you were to fix one of those parameters, I'm going to fix t. T is now a constant. T is not allowed to change. T is fixed. Okay, well, now I have position as a function of, I guess just s, because t is fixed and constant and nailed down, not allowed to change. So position is now a function of one parameter. Oh, yeah, position is a function of one parameter. That's a curve. So this is called the S coordinate curve of that parameterization. That's the big idea. Is that okay with everybody? What do you think? Questions? Okay. Likewise, the other way around, of course. If you were to fix S, now S is constant, not allowed to change. Well, now I have position as a function of, let's see here, just t, I guess. And position as a function of just the one parameter means, again, curve. So when you have a surface, when you have a parametric surface, you can talk about the two different coordinate curves in this way. And let me show you an actual hands-on example. Let's talk about the sphere. We've previously discussed this is the spherical graph parameterization of a sphere. Keep in mind, all I've done here is just interpret the sphere as rho equals 1 and plug that into the coordinate conversion formulas. So, spherical graph parameterization of the sphere. Okay, and that having been set, let's look at this point here, where I've got a couple of values of phi and theta, and let's start looking at coordinate curves. So I'm going to start by fixing phi. All right, we're going to set pi over 6 as the value for phi. So phi is not allowed to change. This angle, phi, fixed, not allowed to change. And with that understanding, and let's see here, also, yeah. So that's fixed. That means that all of this is fixed, and that's constant, and that's constant. And now I want to understand, how does position vary with theta? As I move from that point that I'm looking at, if I move just in the theta direction, well, theta varies, phi doesn't, and I cruise along around the circle like that. So this is called our theta coordinate curve. How you doing? All right? Okay. And then analogously, we have a phi coordinate curve that comes from theta being a constant. And if you think about it, theta, let's see here, if I make theta a constant, theta is the angle that describes planes hinged on the z-axis like that. If theta is a constant, not allowed to change. So, constant, 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 constant. Right, all the stuff in gray, not allowed to change. But now if I start varying phi, okay, well, as phi changes, and I sort of move down the sphere, sort of, head straight south on the sphere. And that's our phi coordinate curve. Happy? Okay. All right. Okay. Now, I'm going to ask a rhetorical question here, which is, what is a partial derivative of a parametric surface. What does it look like if I have a partial derivative of a parametric surface? And I'm gonna kind of walk through what it sort of has to be. Let's talk about the partial derivative with respect to theta. Okay, well, partial derivative with respect to theta. Well, first thing I have to do is fix theta. Right? Fix theta. Oh, no, I'm sorry. We fix phi. Sorry, fix phi. We're taking the partial with respect to theta. So we fix phi. Oh, let me do it like this. Yeah, we fix phi. And with phi fixed, I need to ask, what's the derivative? Phi fixed. What's the derivative now with respect to theta? Well, if you think about it, isn't that familiar? That's exactly how we started off talking about these coordinate curves. So the act of taking a partial derivative of x, step one, fix the other variable, is the same as creating the coordinate curve. Right? Doing a partial derivative and creating a coordinate curve both start with fix the other variable. And so when I say then I want to take the derivative with respect to theta, yeah, well, taking the derivative with respect to theta, that just means I'm going to take the derivative of position as a function of the one input parameter, that's velocity. Right? When you have a parametric curve now, and keep in mind with phi fixed, there's only one input variable, namely theta. That means I have a parametric curve. Derivative of parametric curve is velocity. Okay, so this is the big upshot here, and that is partial derivatives are velocities. Specifically, they're velocities of the coordinate curves. All right. So what we can do with that is interpret something about position differentials. If you think about it, if I were to ask the question, okay, I'm going to move in the from this point where I'm at, I'm going to move in the theta direction by some amount d theta, and I want to know what is the corresponding position differential over here in the on the parametric surface. How do I relate this input change to this output change? Keeping in mind, of course, we're talking about where phi is constant, right? Not allowed to change phi. Well, what I'm talking about then is an input change, output change. They're related by the velocity, aka they're related by the derivative, right? So the this x theta. This is the velocity that relates this amount of input parameter change to the corresponding output position change. So yeah, I should color these differently. Let me color this in blue. Yeah, so d theta in blue there. What do you think? All right. So yeah. So x theta d theta is my position difference. That tells me how far I move across the surface of the sphere per d theta movement in the phi theta plane. And then likewise for the other one. So now redrawing the picture. Here we go. Now I'm going to observe, well, if that input change corresponds to that vector, and if this input change analogously corresponds to that vector, then I'm all set up to talk about the relationship between this area, ds, versus this area, d phi d theta. Right? Because this area, d phi d theta, well, it's just d phi times d theta. It's a rectangle, and this is d phi, and that's d theta, so, rectangles and all. Over here, this ds, well, I'm going to have to do a calculation to see what that area is, but what I have is literally a little parallelogram where I know the edge vectors. So this area over here is an old Chapter 1 problem. Right? Finding the area of a parallelogram in space. You might even call it a Math 218 problem. And we can work out the details there. The DS, see? Yellow. That area there, DS, parallelogram in space, magnitude of the cross product. Specifically, the cross product of the two edge vectors. Is everybody happy? We've got our yellow area that I compute by Chapter 1 methods. We've got our orange area that that's just a rectangle, so by, ninth grade geometry methods. Right? And then a little bit of algebra to make everything kind of come together. Notice that d phi will just factor right out because it's a scalar, and d theta will factor right out because it's a scalar. And in fact, all together then, my output area, ds, relates to this input area, d phi d theta, by this factor. So we have computed effectively, without even kind of really realizing that's what we were doing, we have computed the stretching factor. How much bigger is area on this little piece of parametric surface compared to the area that it came from? And the answer is that area of the output is this factor, the stretching factor, times that input area. Everybody see how we ended up there? Familiar territory, right? Kind of smacks of change of variables and all of that business. And eventually we will kind of be doing pullbacks and that sort of thing. Probably won't get to it today. But anyway, there you go. Okay, so so there's our stretching factor. Now a little bit of lingo. We're going to need to talk about this vector here. The vector whose magnitude is the stretching factor. Okay, keep in mind, area stretching factor is in purple. It's the magnitude. So the vector whose magnitude gives us that is of particular interest. We're going to call it capital N, and it's exactly what it says here. It's the cross product of the two partials of your parameterization. I call this the parametrized normal vector. Normal vector because if you think about it, look at the picture, it is a cross product of two tangent vectors. So it's perpendicular to the surface. So we call it a normal vector. I like to call it the parametrized normal vector because, well, it comes from the parameterization. Right? If you look at the formula for it, it depends on what you're using as a parameterization. And don't forget, just like with curves, there's lots of parameterizations for a given surface. This is not unique at all. You can parameterize in a bunch of different ways. So it's not canonical. It's not intrinsic to the surface at all. It is a consequence of how you have chosen arbitrarily to parameterize the surface. And thus I like to emphasize that by putting parametrized normal vector. Here's where I disagree with the book about one thing. The book prefers to call this the standard normal vector. I just find that misleading. To my ears, standard sounds like they're saying it's canonical or intrinsic. It's not. It depends on the parameterization. Now, this is just lingo. It's not a matter of right and wrong. I just don't like it. To me, it just conjures the wrong images. So be aware, the book calls it standard. I think you'll do better in all contexts if you refer to it as the parameterized unit normal. Everyone will know what you're talking about, no question. Okay, all right. So the parameterized the parameterized normal vector. That is the thing whose magnitude is your stretching factor. And this is a good place to end it. We are going to see an example, first cat out of the bag next time. And basically, we're all set up to start doing surface integrals. Y'all have a great weekend. Try to stay dry. And then later this weekend, try to stay warm. See you later.